Okay, I think we should begin a webinar today. And yeah, so good morning, early morning in London, and good afternoon in Taiwan. And today is really my great pleasure to have Dr. Li Dongchen from Imperial College London to present his result on the persistence of heterodimensional cycles. And this result has already been published in Invention. And if you are interested, you can find more detail on, on the internet. And today he is going to tell us his insight on this problem. And we are very curious about this. So let's welcome him.
Thank you. Okay, so thanks for the invitation. I'll start. I'll start with some motivation first. So there is, to me, the fundamental goal of dynamical systems is just to understand the dynamics globally. So there can be very simple systems, such as Morse-Mel system, and there can be very complex systems just by, for example, some simple mechanism, a local mechanism called transverse Hopkin intersection. It was discovered by Poincare like nearly 100 years ago. If you have such robust mechanism and very simple, you will get very complicated dynamics. So the task to understand the dynamics globally, it kind of becomes very tough. It's not very non-trivial. And to better classify the dynamics, Smale, he introduced the notion of hyperbolic systems in 60s. What is a hyperbolic system? It means that the D field F it satisfies two conditions. First, it is extreme A, and also it satisfies the no circle condition. So extreme A means that the non-wandering set of F is a closure of the period orbits, and also the set is hyperbolic in the sense that its tangent bundle admits this ES plus EU splitting, which you have this stable bundle and unstable bundle. And vectors in the stable bundle is contracted by the differential df, and the vectors in the unstable bundle is expanded by the differential. So this non-random set, it must be hyperbolic. Then the system is called XMA. And there is a very famous spectrum decomposition theorem by Smale, which says that if your system is XMA, then its non-wandering set, this omega f, it decomposes into finitely many hyperbolic basic sets. Basic here means it's compact, transitive, and locally maximal. So that's the no cycle condition means that there are no cycles formed by the basic sets in the decomposition of this non-wandering set. So but basically it means that you don't have hash dimension cycle. So then the D field is called hyperbolic. To be hyperbolic is a very good property because the restriction of the dynamics to the non-wandering set is structurally stable, and also the set of all hyperbolic D fields is open. So there was a very natural question, could we say a hope that hyperbolic systems are dense in the space of different morphisms? Because then it's going to be, we will have a very good picture of the dynamics, right? But it's not true. Of course, in dimension one, we have this remarkable result by Kolowski, Shen, and Van Strand, who showed that actually in dimension one, we indeed have such density. However, in higher dimension, we do not. So let us first observe two very simple mechanisms which are obstacles to hyperbolicity, right? So The first one is called homoclinic tangency. I'll just write it like HT in the following. So I think you must be very familiar with this thing. It's been discussed very intensively in many areas. So suppose you have a saddle, which I mean a hyperbolic periodic point, and it's stable and unstable manifolds they intersect non-transversely. Then you see that you have a tangency, homoclinic tangency to the saddle. And the second object is called hadron cycle. It's actually the main object I'm going to discuss in this talk. So here you need to have two saddles of different indices. Here by index, I mean the dimension of its unstable manifold. So that we have two saddles of different indices and their invariant manifold intersect cyclically, which means that, okay, I'll just show you the picture. The simplest case of a Hershey-Dimensional cycle is like this. So you have two saddles, P and Q, and they have different indices because P, the unstable manifold of P is one-dimensional, and the unstable manifold of Q is two-dimensional, right? So, and they intersect each other, so you have a cycle. So by the difference dimension, you must have one transverse intersection between the stable manifold P and the unstable manifold Q, right? So, and also you must have one non-transverse intersection between the two one-dimensional stable manifolds. But it's the whole dimension is 3, so the intersection between the stable and unstable manifold, the stable manifold of Q and the unstable manifold of P is non-transverse, which means that it's very fragile. It's just like a tangency, which you can remove it by an arbitrary small perturbation. Right. So if you have such an object, such a cycle, your system cannot be hyperbolic because the heteroclinic orbits which connect the 2 points and along with the 2 points, they belong to the non-boundary set of the map, right? And also, so now near the cycle you cannot be hyperbolic because there's a central dimension. Near P, it's stable, it's contracting, but once you move from P to Q, the central dimension becomes unstable. It will expand. So you cannot get ESEU splitting of bundle. So the non-boundary set is not hyperbolic. So your system is not hyperbolic. But you say if you only have these two objects, you cannot see that they imply the hyperbolicity is not dense because you need to show that actually the two objects are robust, right? And indeed, they were shown that the good examples first that you have robust tangency and robust Hershey-Dimensional cycle, which means that in the space of different morphisms, you can find open regions where you don't have hyperbolicity. So it shows that we don't have a positive answer to the question that hyperbolicity is not dense in higher dimension. And now I'm going to define what's robust tangency and robust cycle, right? Because by Kupka-Mayo, we know that still generically, this invariant manifolds saddles, they intersect transversely, right? So it cannot happen that if the cycle, for example, the tangency to a saddle, it cannot be robust, such as by Kupka-Mayo. So we need to define more generalized Hershey-Dimensional cycle and tangency. So we just replace the saddles in the previous definitions by hyperbolic sets. So for example, for say a robust homoclinic tangency, we just see that we consider a hyperbolic basic set lambda, and we consider the tangency, the non-trans. We see that this set, hyperbolic set, it has a homoclinic tangency if it's stable and unstable sets, they intersect non-transversely, so that you have a stable leaf of this set and an unstable leaf of this set, they intersect non-transversely. You have a tendency between the two leaves, and it's called robust because this compact transitive hyperbolic set, it has unique continuations for all nearby systems, right? So you can consider small neighborhood of the system F in the space of diffeomorphisms, right? If you can find a neighborhood such that every map in this neighborhood always have a tendency to the continuation of the hyperbolic set, then you see that you have a robust homogeneous tendency to the hyperbolic set lambda, right? So it means that you cannot remove the tendency. So it's robust. Similarly, for Herschel dimensional cycles, you just remove at least one of the two saddles by a hyperbolic set, right? So you can then you can talk about the continuation of the hyperbolic set. You can see that in a small neighborhood of F, for any J in this neighborhood it has a Herschel dimensional cycle with to the continuations of the hyperbolic set and the saddle of another hyperbolic set. So it's called robust Herschel dimensional cycles and robust tendencies. And also, I want to mention another terminology which also used in the literature is called persist. So we see that so it's a consequence of being robustness, right? So it means that you can find an open region where it contains a dense subset, such that each map in this subset has a tendency of cycle to saddles, right? So because for basic sets, the periodic points are dense, right? So if you get a robust tendency to a set, basic set, you can just pass arbitrary small propagation to put the tendency to any saddle inside of this set. The same for the cycles, right? So this robust Herschel cycles and robust homogeneous tendencies. So as I just mentioned, very soon after the question were posed, there were examples of robust tendency. The first example was given by Neuhaus in 70, I think yes, 70. He showed an example of C2 surface diffeomorphisms where you have C2 robust tendency, and later, like 79, he proved that actually such robustness is very abundant, in the sense that for any for any diffeom surface diffeom which has a tendency to a saddle, but you can find by an arbitrary series multiplication another map which has the C2 robust tendency. But what's important here is C2 robust, but it's not C1 robust. I'll talk about this later. Return to this later. And also, this result was generalized to higher dimension by several people. And similarly, for the Herschel dimensional cycles, actually, Abraham and Smale, they constructed the example of C1 robust Herschel dimensional cycle in dimension 4, also in 70. And later, by Bonatti and Diaz, we know that actually, okay, I forgot to mention that the co-index. The co-index of cycle is just the difference between the indices of the saddles P and Q. So what I showed you in the picture is just the cycle co-index 1, right? Because one, the index of Q is 2, the index of P is 1, so the difference is 1. So they show that if you have a cycle co-index 1, two saddles, then you can C1 approximate it by another diffeom which has C1 robust Herschel dimensional cycle. Right. These are all the previous results, and based on those results, we have some conjectures I want to mention. The first one is the partial density conjecture. This one is actually before the results by Bonatti and Diaz, right? So it conjectures that diffuse which has either a tendency or cycle or CR dense in the complement to the closure or the hyperbolic ones, right? So either your system is can be approximated by hyperbolic systems, or it can be approximated by systems which has a tendency or hash dimensional cycle. And there are a lot of progresses in the C1 topology actually. For example, this has been proven for R equal to 1 and for surface diffeomorphisms very early. And later by Corvisier and Gels, they show that if the dimension is larger than 2, then it's true it's true if you replace the hyperbolic by a weak form hyperbolic, then they show that then it's also true. But it's all in C1 topology. And later, Bonatti, he proposed, based on his result with Diaz, he proposed another version, a stronger version of this conjecture. He stated the conjecture in C1 topology, but now I think it's also okay to state it's for CR topology, so I just change the topology to CR. So it means that it said that in space of CR diffeomorphisms, you may have 3 open sets, right? One HR, which means that the maps are hyperbolic. HT means that the map has a robust homogeneous tangency, and HDC means the map has a robust hash dimensional cycle. So that's the union of the sets that open and dense in the space of CR diffeomorphism. It's a conjecture, right? So our results, actually, in a way, our results support this conjecture, and the main results of us is this. As I mentioned, that TDR they showed us near any cycle you can approximate in the C1 topology by those having robust cycle, but we show that we improve this the results by showing that actually it can be approximated in any topology. So it can be CR to infinity, and it can be real analytic. And the methods are different, and I'll show. So before I go to the setting, I'll show the yeah, I mentioned the main mechanism. Yeah, the mechanism for robustness is called Blender, which was introduced by also by Bonatti and Diaz in '96. A Blender is a special hyperbolic basic set such that the projection of its stable or unstable set along the strong and stable or strong stable foliation. For example, the stable set of lambda, the projection of a stable set of lambda along the strong and stable foliation has one more topological dimension, right? So if, for example, if your map is 3-dimensional, your stable, your stable manifold of lambda is 1-dimensional, but after you project it, it contains a 2-dimensional disk. So that's it. Your 1-dimensional stable manifold becomes 2-dimensional in the projection. So that you can create non-removable, non-transverse intersection between the stable set and another one-dimensional curve, which I'll show you later in pictures. So basically, it means that finding robust hash dimensional cycle is equivalent to finding blenders. And the difference between our results and their results in C1 topology is following. In C1 topology, what they do, their prediction is essentially only valid in C1 topology because they do a complete linearization near the set, which can only be achieved by C1 topology. And also they use this Frank's lemma and Hayashi's connecting lemma, which are both only valid in C1 topology. So their method cannot be transferred to the hair topology. And also to create the blenders, to create the robust hash-diagonal cycles, they must destroy the original cycle. But in our method, we do not do such linearization. We do nonlinear analysis with zero perturbations, and we also identify a class, three classes. Okay, one class of hash-diagonal cycles where you have blenders near the cycle. You don't need to perturb actually. Once some condition is satisfied, the cycle is there. You don't need to unfold the cycle. No perturbation is needed. Then you have find blenders. And in some cases, you don't need to do anything. Once the conditions are satisfied, the cycle is automatically robust. Here's just the main difference I want to mention. So I can now start to introduce the setting. Okay. So we consider a hash-diagonal cycle. We view a cycle as a union of four orbits. Two periodic orbits, which are used to define cycles, and we also take two heterogeneous orbits to intersection between their manifolds, right? We have this non-transverse intersection. For example, we just assume that for simplicity, we say we are in a three-dimensional case, and L1 is just the orbit or the previous point P, so it has index 1, and L2 has index 2. So the unstable manifold of L1 is one-dimensional. The stable manifold of L2 is one-dimensional. So we have this non-transverse intersection. We take a heterogeneous orbit from it, we call it gamma 0, and we'll take another heterogeneous orbit from another intersection, which is transverse. So it's two-dimensional, they are transverse. Yeah, so we have three cases depending on the central multipliers of the saddles. Okay, so you can just we have they have this lambda, the stable multipliers, the gammas are stable multipliers. But you look at the so in general position, you can assume that here you have this strictly larger, strictly less, right? So you only look at the central multipliers. You care about the for L1, whose index is smaller. You care about the central stable multiplier, this one, and for the other side of this one, you care about the central unstable multiplier. So it can be both real and one real, one complex, or both complex, non-real. I mean, so you have three cases. The first case is, we call it saddle case, which means that the central multipliers are both real. So it's shown in picture A. So you have all real eigenvalues here. You have this, you see a strong stable manifold and strong stable manifold, and one-dimensional. So on the saddle focus case, which means that one is one central multipliers. For example, here the central stable multipliers of this L1 is non-real, it's complex, and the unstable multiplier of this one L2 is real. And the last case is we call double focus case, because here we have two focus right? So here the central stable of this one is non-real, central unstable multipliers of this one is non-real. Yeah, so we have three cases. What do we do? So as I said, we consider the four orbits, right? The four orbits form a cycle. So we can just consider the first return map along the whole cycle. So first, for now, I'll just discuss this first case, the saddle case. Right. For all other cases, actually, we just we do computations and we reduce to the saddle case. So for the saddle case, let's say we have two periodic points, O1, O2, right? So we have here, we just we consider coordinates near the 2 points where the manifolds are straightened. So you see here, along y direction, here is unstable manifold, one-dimensional. Here the two-dimensional manifold, two-dimensional stable manifold, or two-dimensional. And here one-dimensional stable, two-dimensional unstable. And we have two one transverse intersection. This piece is just the map F21. F21 is a transition map along the transverse clinic. So we take 2 points, M1 plus and M2 minus. There are 2 points of the transverse hedge clinic. So there is F21 transition map is just some iteration of the map which takes the point M2 minus to the point M1 plus, right? So F21 takes a piece of this unstable manifold here. So we have this, it transfers to the strong stable leaf, which goes through the point M1 plus like this. And we also another transition map F12 along the along the non-transverse hedge clinic. So it takes a point inside the hedge. We have 2 points and 1 minus and 2 plus in the non-transverse hedge clinic orbit. So F12 is also some iteration of our map S. It takes a point and 1 minus to the point M2 plus, right? So you have this 2 intersection here, that to one-dimensional. So what you consider? You consider you start from this point and 1 plus, right? So you iterate it near O1 by our map. So F1 just iteration F period L1. You iterate. You take a small neighborhood of this M1 plus. You take a point inside it. You iterate. It goes here. Here it go up. Here you have expanding in Y, right? It goes up. You go to a small neighborhood of this point, and then you apply. You apply transition map F12. Go from the first saddle to second saddle. Goes here, and then you iterate because here you have contracting. So it goes down and goes out. It goes here, and then it goes back along the transition map F21 from here to here. Of course, it's not it's not always that you can come back, right? It's important that how many times you iterate near O1 and how many times you iterate near O2. So it's very important to choose the values of K and M, the number of iterations, so that you can return. Right? It's not automatically you can return. It's possible that you just iterate to somewhere else, right? So the key point is just the choice of the integers K and M. And actually, we show that.
Sorry, Dongsan, I have a question. Can you go back to so
okay.
What are the transition map F12 and F21? Can you remind me? Why is F12 F2?
Okay, F12 because you have this hedge clinic intersection between the unstable manifold of this O1 and the stable manifold of O2, right? So you can take a hedge clinic orbit.
You follow the hedge clinic orbit. Yeah.
Yeah. So and you take 2 points and 1 minus from the hedge and M2 plus from the 2 points from the hedge clinic orbit. So that's because they're in the same orbit. So there is some iteration of F which takes this point to another point.
Okay, thank you.
No problem.
Sorry, I have a question. So, but this question, this picture only holds when you have a saddle, right? When you have a saddle.
Yeah, you're right.
Saddle focus, and this is not the case.
Yes, it's not the case. It's if you are in the saddle focus case or double focus case, it requires more computation. The picture is not same, but in end you will always find something like this, which I'll tell you now. So the thing is that you can find coordinates near this point and 1 plus where near which we define this return map TKM, right? We define this map near this point. So you can find coordinates near this point such that there is a cube of set delta is very small, and a sequence of pairs K and M, right? And you can show that in these coordinates, the return map it takes x, y, z to x bar, y bar, z bar, if and only if this relation is satisfied. It's actually written in the you see here. But yes, we have this central direction. And Z is a strong. I can see the picture. Z is a strong, stable direction, and Y is expansion. Right? Expansion, strong, stable, stable. But once you come to here, right, the central direction X is mapped by some transversality condition. This direction is mapped to the U direction. So here you are contracting here, and once you go near saddle O2, you are expanding, right? But this unstable direction is mapped to the strong unstable direction. So in this direction, you are always expanding. This Y is mapped to W. You're always expanding. This Z direction is mapped to the V direction. So you are always contracting. Only the central direction, this one-dimensional X, here contracting and here expanding. It means that here you are contracted K times near O1, but here you are expanded M times near O2. So there is a balance between this M and K such that you can achieve some contraction in the central direction for the whole return map, or it's expanding, and which is very important, which I'll explain now. So you find this formula for the return map. As I just said, in Y direction you have contract expansion. In Z direction you have contraction. But here we write the formula in the cross form, so that you see the pre-image is Y is actually the function with image Y bar. In this way, the right-hand side here is a contraction. So it's gonna be it's easier to do the later computation. So we write it in the cross form. And what's important is this central direction. It's one-dimensional dynamics. It is what actually matters. So we have this. You can see it's nearly affine, right? So the property is that all the functions phi are very small with their first derivatives and this, and the coefficient in X that bounded away. So bounded that either between 0 and 1. So it means that in the central direction you're contracting, or that between 1 and infinity. So in central direction you're expanding, right? So it's the second condition. And third condition is also very important, is that the constant terms here, Bn, they form a dense set near 0. From dense set near 0. And the third one is that the right-hand side, it takes the cube. The cube, you can see that it's the cube of the delta, right? So it takes the cube inside the cube, which means that you can find a local set which is inside the pi, so which is will be the candidate of Blender. So this means that the dynamics for all points near the box is actually conjugated to the symbolic dynamics, the full shift of some symbols. So what we're gonna analyze is not all the sequence, the whole sequence. We just take a finite collection of pairs, which will be chosen appropriately, so that we get Blender. So we just need finite many pairs here. So for example, in the simplest case, we just need.
So I have a question. Can you go back?
Yeah.
Is there a typo like in your left-hand side? You should X bar, Y bar, not Y, but Y bar, and to the right-hand side is Y or Y bar.
Yes, Y bar. So I mentioned that it's called. We do this intentionally.
Intentionally.
Yeah. It will help in computation a lot. So because in Y we have you see in Y we have expansion, right? In Y we have expansion. It means that you see if we consider a box, Y is so we know that so that's the right hand side is defined on the cube pi. So if you see this picture, we have the cube. If you rest the map in cross form, then the right hand side is defined for all the finite values here. So it's actually the right hand side is a contraction, so that we can show that.
I see.
Because of this, we can. Yeah.
So can I say you want your right hand side to mean contraction? And because you have a saddle, so one of the direction is expanded. So instead of considering y bar to the left, you consider y to the left.
Yes. Yeah, right. So the map on the right hand side is a contraction.
Okay. Interesting. Okay. Thank you. Yeah.
Yeah. Okay. So for example here, as I said, we choose finite many pairs Km from sequence, right? So it's gonna be chosen properly, right? So now depending on it, how many pairs you need depending on the A here and the system, but you can always find a finite many with them. So that's you'll see later why. So for example here, I say that I only need 2 pairs. So I need 2 pairs. We'll have 2 return maps. Okay. And I assume that's all the AN here, the coefficients here, they belong this small one, right? Which means that in the central direction X we have contraction. Right. We have contraction for here, smaller than 1, we have contraction in X. Okay. So we'll take 2 maps, and this one map takes this horizontal strip, whereas in horizontal strip to the vertical strip to this one, and the other map takes this horizontal strip to this one, right? And we can see that when we define another map G is defined on the union of domains of the 2 map to map TKM. So it's G defined. Sorry. G defined on the union of 2 strips. But if the points in this strip, we apply the 4th return map. If it's less in this 2nd strip, we apply the 2nd return map. And we can show that the locally maximal set of J inside this Q is the hyperbolic basic set. It's very easy because just by a formula, we can show that it's a conjugate. Actually, the set is all point. It consists all points whose orbits do not leave the cube. Right. So it's actually the dynamics on the set is conjugate to the 2 shift of 2 symbols, and especially we note that the unstable manifold of this set, this lambda t, which will be our blender. This set is one-dimensional because you have one dimension as expanding. It's one-dimensional, and it consists of points whose backward orbits stay in pi. Right. So now for now we get a hyperbolic set, and now and then we'll prove that this hyperbolic set is a blender. I didn't give a definition of blenders, but now I'll define the bad property, and you'll see here. So we take out the 2 return maps such that we can find a subcube, this one, inside the previous cube, such that we can also define the image by J of the subcube. So that we take the intersection of this subcube with the 2 horizontal strips, and their image are this one. And that chosen so well, such that if you only consider now, you take this subcube out, and you take the image of subcube out. You see that what you see. You see the image. The images, the 2 vertical strips, they cover the union of 2 strips. They cover this subcube in the central direction, right? This x direction, central direction. You know that in central direction you are contracting, right? But still, you're contracting in but you have more than one images, so together they cover this subcube in a central direction. It's what we need, and it's what we can get from the sequence I just mentioned. So now just assume that we can do this, we can cover this central direction just by 2 return maps. And then I can define if the maps, the 2 return maps are chosen, what I shown that such that we have the picture here. Then we see that the hyperbolic set lambda t, which we just defined, is a blender CS blender. CS means central stable, so central stable will have stable. Why? We call it. It has what properties? It has properties that as a disk, you can imagine it's one. For example, in the system case, it's just some disk along nearly parallel to strong stable direction. Because you see here you have this your set is hyperbolic, so you have this strong stable cone field, right, near your hyperbolic sets. The strong stable cone field is around this Z direction. The cone field is nearly parallel to Z, so that you can just send this vector that's for any curve here, which is nearly parallel to Z direction. If it crosses the cube here, the subcube here, it will intercept the unstable manifold of the set lambda, the blender. But just recall that we just mentioned the unstable manifold of lambda is just one-dimensional, because you see we just have one dimension expanding. But so you have this, and you get this cube with this. It's an open set, right? If you move your curve a bit, you perturb a bit, it still crosses this cube, right? So it means that you always have the intersection between the one-dimensional curve and the one-dimensional unstable manifold. So they are robust. The intersection is non-transverse, but it's robust. Okay, so I'll show you how we get this property. It's very simple, actually. So suppose you have a one-dimensional curve, which you see you go across this cube like this. You, along the Z direction, you cross the cube, right? So it must intersect one or 2 images here, right? Because you see, the 2 images, the union of 2 images, it covers the cube, right? If you cross like this, for example, you cross the first cube, right? Because it's an image. It's an image of this horizontal cube. So right, if you consider per image, you'll get the intersection of your curve with this cube will again be a curve which goes from here. It will again cross this subcube like this, right? So you can repeat this procedure, and so this will cross one of the 2 images, right? Then you can do again. So you consider the per image again, so that in the end, you can find a nested intervals or compact sets on the curve, this curve, such that for each interval, the image in each interval after some iteration is as a disk, right? It is a curve crossing the cubes, which means that because the compact, right, and nested, their intersection is not empty. So you'll find at least one point. Actually, there is exactly one point here. So you have one point in the intersection, such that the intersection has infinite many pre-image inside the cube, which all the backward orbits of this intersection point always lies in this cube, right? So by our definition, this point must belong to the stable manifold of lambda, right? So it shows that on the curve which crosses this cube, it contains such points, so that you have an intersection between this curve and the unstable manifold of lambda. So we have constructed blenders. Now we see that actually once we get this blender, it's very simple to get a robust hash-down cycle like this. Right, suppose here you have another cycle P. Here is the box where we have the blender, right? Okay, I need to actually use Q here because Q has index 2. Here, sorry, so the point here is a two-dimensional unstable manifold like this. So you remember here is and one-dimensional stable manifold like this. So just as what we said, if your stable one-dimensional curve it crosses the box along the z direction, strong stable direction, it will intersect the unstable manifold of the blender, right? And also the stable manifold of blender, see, because it just like parallel to this XZ plane, right, subspace. So of course, the stable manifold of lambda will intersect the unstable manifold of P transversely automatically. So that now you just get a robust hash-driven cycle because the transverse intersection cannot remove, right? Just by definition. And the non-transverse intersection, because this curve it goes into blender, right? So the intersection between this curve and the unstable manifold of lambda is still cannot remove after small population, so that you get a robust hash-driven cycle between this point P and the blenders here. This is how you get the blend robust hash-driven cycle. And what's important is that I want to say that what we proved for the approximation of robust hash-driven cycles, and the existing blender is also very important. Actually, we show that, as I mentioned, you don't need to do perturbation actually once some condition is satisfied. So we proved that actually also if some arithmetic property is satisfied for some moduli, then you have blenders automatically. You don't need to do perturbation. So for example, here, this recall that this lambda 1 is just a central stable multiplier of the first set of O1, and this is the central unstable multiplier of the second set of O2, and this omega 1 2 are just the frequencies, right? So okay, so for non-degeneracy, it means that some transfer conditions are satisfied. So it's kind of obtained by average small perturbation. And type 2, it means it's a subcase of the case of the saddle case, right? So I don't want to elaborate here. It's complicated. It just means that in the central direction, some orientation preserving condition is satisfied, right? So if it's not in this case, then the cycle is accumulated by blenders. Actually, you can find the we call the nearly affine blender system, just the system of the maps. I just showed you the maps, TKM maps. You will find such maps near the hash-driven cycles, which means that you get a sequence of blenders accumulating on the cycle. You just need to check if this ratio is irrational or not, if this ratio is irrational or not, like this. So if they're all rational, I mean, this is rational, this this is both rational, then generally you don't have blenders. You only have two hyperbolic sets actually in your hash-driven cycle for any perturbation. So it's kind of you can get a kind of full understanding, full picture of dynamics in your hash-driven cycles. And our results are all obtained from parametric versions, right? So actually, a good thing that you can verify the existence of hash-driven cycles and blenders just by computations. But you can just you only need at most 4 parameters. In a double focus case, we only need 4 parameters, right? The mu is just it controls the unfolding of the non-transverse intersection, right? And the mu equals to 0, it means that you have this non-transverse intersection of the cycle at the beginning. When you change the mu, the cycle unfolds, you don't have it. And here's theta, the ratio I mentioned here is this log lambda or log gamma minus. So in settle case, you have two. You need two parameters. Instead of focusing in the three, double focus you need four. Actually, this was improved in new paper, which in the paper also for all cases you only need two parameters actually to verify if you can get into an open. Okay, if you have those parameters, you can show that in the space parameter value parameters, you can get open and then I don't know. So sorry. In the space parameters, you can get open regions accumulating to zero. That's where you have the blenders and all stuff, robust hash dynamic cycles. Okay, this is the parametric word. I will just get open regions in the parameter space, right? For which you have this C1 robust hash dynamic cycles and blenders. Okay, second, this is about the stabilization. So people care about if the robust hash dynamic cycles cycle you obtain from previous one is connected to the continuations of the saddle of the cycle where you start, right? So there is one type. If it's not type one, so we can show that the continuations of the previous saddles are all homogeneous related to the sets in the robust hash dynamic cycles which we get. Okay, so I'll just mention one thing. That's some application of the with nearly affine blender system with finds near hash dynamic cycles. It's kind of improve. If you remember, Newhouse has proved that Newhouse shows that near any tendency to saddle, you can find a robust tendency, right? But the tendency can only be C2 robust. Actually, by result by Moreira, it shows that okay, the Newhouse construction it relies on the two-dimensional horseshoes with large thickness, right? And Moreira shows that there are no C1 robust tendency to any two-dimensional horseshoe. So this is a strong indicator that the Newhouse construction does not work for in C1 topology. So if you want to get C1 robustness of homogeneous tendency, then you need some new mechanism. Actually, Bonatini and Diaz, we know that from a standard blender horseshoe, you can get C1 robust tendency, but to get such objects, this blender horseshoe, you need C1 coefficient. So, but in our by our method, you can create some generalizations of this blender horseshoes by serial propagation. And I show that if you have a homogeneous tendency to a saddle, which has effective dimension larger than 2, it means that the central it basically means that the central dimension is larger than 2. Right? Because you see here, if the two-dimensional case, actually two-dimensional construction does not work. And we need you to use blender, but blender is some object which only live in three-dimensional or higher, right? So here is it means that the dynamics in central direction is not two-dimensional. And if this is the case, then F can be still approximated by a D field which has a C1 robust homogeneous tendency. So here it improve the C2 robustness in the previous Newhouse result. Oh, this is one application here. What we do here, which just by another result, we create hash dimensional cycles near such tendency. Then we use the blenders, which we found near these cycles, to get this robust tendency. Okay. And this corollary is just you can get this get this a set U such that for generic maps in U you have this they have infinite many things, right? But previous result it's just C2 open by the previous theorem. But we can show that it's also C1 open. Okay, so it's just a very small improvement over the previous result. And in the end, I want to mention this result because it was conjectured also by Python. For a typical, but you only have finite many attractors, but in the space of diffeomorphism, right, there is not canonical measure to, right, in space of diffeomorphisms. So that's it's you need something to see a system is typical, right? So there are many notions to define typicality in the space diffeomorphism. One of the following is this, which actually this is result by Barrett first. He showed this existence of this domain, which disproves the pulse conjecture or some conjecture of Pugh-Schuh, which said that a typical system, right? It has only finite many attractors, and it must be interpreted at least now by this typicality, because in the topological sense, it's wrong already by the result of Neuhaus. So we consider here an open set in the space of families of diffeomorphism. Right here is a key parameter family. Right, this parameter space to a space of diffeomorphisms. Right, it's called a CDRK Barrett domain if generic families. So if you have in this set U, it display infinite many things. So it's attractors, right? Infinite many attractors for all parameter values, which means that if even you remove parameters for whole parameter values, you have infinite many things. So it shows that at least for the open set U, the existence of only finite many attractors is not typical. So the phenomenon is not typical, right? So actually, how better prove this existence of such domain? He did an example. He constructed an example where he used a parametric version of Blender. So he considered a family of Blender, so which he called parablenders. And we can also show that the blenders found near Hertzsprung cycles in our paper, it can be embedded to a family so that it becomes a parablender, so that we can also produce such phenomena. So we can show that if you have a homogeneous tendency to a sync producing cycle, just I mentioned that if you don't have strong and stable direction, right? You need to produce attractors. We cannot have strong stable direction. You don't have strong stable direction, and also the central direction it contracts volume. So you have a sync producing saddle and effective dimension less than 2, which means you can produce Blender by some Hertzsprung cycles. Then you can find an arbitrary closed map G such that the constant family G of G is less automatically less in a Barrett domain like this. So which means you can find you can find that near such a map, you can show that a typical map near such a map as it displays infinite many things like all parameter values. Okay, I think it's all for today. Thank you.
Oh, thank you very much, Dongchen, for, I would say, very deep talk. Okay, thank you very much.
Sorry,
so,
I went too fast. So,
yeah, very nice, very nice. Thank you for giving us so many new ideas. So, any question, comments, remarks from the audience? Just unmute your microphone and just ask, please.
Yeah, I'd like to ask a question.
Please.
Yeah, can you go to the page 7?
7, okay.
Yeah, I just want to ask about this conjecture of Bonatti and so you have this union of these 3 sets.
Yes.
So there's open intents in the space of this diffeomorphism. But I wonder what is so if there's a map which is not in this union, what is the typical dynamics?
For example, if
it's not in this union, there's no robust. Oh, okay, it's robust. Okay, please, yeah, please.
Yeah, please. You can imagine like the tangent bundle. You have this the angle between the stable and unstable bundle. For some orbits, they become arbitrarily small. You can become arbitrarily small, but so you cannot have this uniform hyperbolicity, right? But you can also you don't know if you can create tangency.
Okay.
Right. In such case, like.
Okay. So we don't know.
They have a paper with Pujals, Blantidia, right? They have this C1 dichotomy, right? C1 genetic dichotomy for diffeomorphisms. In that case, they consider what I mentioned. You have these angles between the bundles that get arbitrarily small. They don't create a tangent from that. They actually they create sinks of that. They perturb. In C1 topology, they get saddles with eigenvalues on the unit circle, and they perturb so that you get sinks, but they don't get tangents.
Okay.
So it's a question whether you can get tangents from that.
Okay. I see. Thank you.
No problem.
Thank you. Other question, comments, remarks? Maybe let me ask a very fair question. Can you go to your main theorem? Maybe there's like a C2 factor diffeomorphism. Yeah, here. Yeah. So this statement is ABC, let me call C2. Diffeomorphism can be approximated by C1 robust. And can you really mention if I just consider C2 robust approximation, then the proof will be very easy or not? If I weaken the regularity requirement.
Where you mean here? On R2?
So here.
Only 2.
Yeah. So R is 2. And now C1 robust. Okay? My question is now if the theorem now becomes C2 robust, is it possible?
It's because you see, C1 robust is stronger than C2 robust, right? So we get blender. Once you have blender, you always have this C1 robust thing, right? So the only difficulty is to increase the approximation here, the topology here. In C1 topology, you have tools like I mentioned. It's complete. This flux lemma, this connecting lemma, those you don't have in topology. So in third topology, you really need to else.
So my question is now we have a C1 robust cycle, and then if I only allow C1 diffeomorph approximation, then there's a counter example. Or not?
Sorry, can I see again?
like if I just consider R is 1, like C1 approximation, and it's
Yes.
impossible, there's a counter example.
Counter example. What do you mean counter example?
No, sorry. Your statement is ABC R diffeomorphism. R is bigger or equal than 2.
Yeah.
Right.
Actually, you see here. Here you can write R equal to 1 because for any C1 diffeomorphism, you can just first approximate by you can do approximate by a real negative map, right? So actually you can start from 1 here. There is no problem. You start from 1 here. But what I want to mention, because we have this pragmatic version, if you do the pragmatic version, it requires at least 2 here. 2 or 3, I forgot. But it doesn't matter if you don't consider parameter families for the main theorem. Like here, you can start from R equal to 1.
Okay, thank you. And maybe this question is so a little bit fake, but maybe you can give us some. So suppose, for example, we study PDE like continuous dynamical system, smooth dynamical system. In which situation can we apply your result?
Like so can you elaborate? Because I don't have much knowledge in PDE.
I mean, I am thinking, for example, we can consider Poincare map, right? If we want to find periodic solution and the local dynamic is captured by the diffeomorphism on the Poincare section.
Yeah, it's what I didn't mention. That's our result applies to the continuous time case because actually
apply to what?
The continuous time case.
Yes. Also.
Yeah, because you see here, what we do in our proof, we only consider this map, the composition of for local maps, right? You don't need a cross section which on your whole manifold. You just for example, you get 2 periodic orbits, right? In this for some flow, right? You can just consider the time period. So F12 are just the time period shift, right, near the period orbits, and F12 it's just the map which follow the trajectory from this point to this point. Yes. Yeah, so it works in the continuous time. Yes.
Very nice. Then now my next question would be: today you are talking about the dimensional cycle between between fixed point or steady state, right? You have the O1 and O2. I think they are fixed point of the diffeomorphism or
it can be periodic points. Yeah, it just need to consider periodic points.
So, it can be periodic point, like periodic orbit.
Of course.
Okay. So I see. So you consider like a heteroclinic connection between 2 periodic orbit.
Yeah. It's just so a hash thermal cycle, just a hash clinic cycle, which has some special properties, right? So
okay, interesting. Okay, cool. So other questions, comments? Okay. If it is not the case, I think I'll speak Dr. Li Dongchen again. Yeah. If you want to stay and have some private discussion or chat, you are very welcome to stay or see you next time. Okay. Dongchen, thank you very much.
Okay. Thank you. Thank you.
Wow. Yes. 现在那边已经10点、11点了，10点。
对。刚10点。我怎么头发还
伦敦现在天气怎么样？
还挺冷的。前阵儿挺冷的。你们那边怎么样？我看你还穿短袖。
我今天比较冷一点。对，穿短袖。我昨天32度吧。
哇，那是我们这一半都不到，我们这有时候早上就7、8度，挺冷的。
对，我现在在那个，你有来过台湾吗？
我还没有
没有，
去过。
是。刚刚那个陈一全老师，我觉得他就是做比较像这种动力系统了，他做 Julia Said，你知道 Julia Said 的
哦，
一
那自动
些，
系统对吧？
对，动力系统。那我的话，台湾就是做这种比较离散动力系统 Diffeomorphism 的，或者 Symbolic Dynamic。台湾有时班龙超老师，我不知道你有没有听过，还有就是陈一全老师啊。那其他人大部分都做 PD、OD，对。
对，因为我也看好你是做那种流里边的东西比较多，flow
我是
的东西比较多。
做其实你就把它体验成 PD，只是说它有一些 symmetry 啦。那因为有一些
啊，
symmetry，所以我可以去 consider spatial solution，就是例如什么传动波、traveling wave、rotating wave。然后我的研究比较有意思的，就是说，你看嘛，我们数学家都是说，我现在有个方程式，我就开始解的存在性嘛，然后
嗯，
接下来就问解的稳定性嘛，或是去看它
对的，
stable invariant manifold。那如果有 center part，我们就考虑 bifurcation 嘛，大概是这样。
对，
然后我做一个比较有意思的事情，是说，假设我有个 solution 是 unstable，OK，就是你有个 eigenvalue 十不大于零，譬如说。然后我引入一个 control，就是这个 control 基本上就是在我的方程里面加一个东西，然后这个 control 有一个特色是你本来的解还是新的 control 方程的解，但是这个 control 可以去改变它的稳定性的。就你假设有个
哦，
不稳定的解，现在加这个 control 之后，它不止没有把你的解给破坏掉，它还改变了
它变成稳定了。
你的稳定性，它
哦，
可以让你变稳定，从不稳定变稳定，或从稳定变不稳定。哎，那
那挺厉害
application
的。
的话，就是说你本来有一个方程式有 unstable solution，那代表说你根本看不到，因为它 unstable，你 perturbation 就跑掉。然后现在把我的 control 弄进去，这个 control 基本上一般情况下是很便宜啊。另外一个就是它所需要资讯很少，那我可以改变 stability，让你可以看得到它，这样子。对。
明白，大概我对这方面不熟悉，但你说的挺清
没
楚，
有没有，
大概知道是
只是
什么用处。
对，所以我觉得你的今天的结果很难呢，因为你处理的事情是一个呃很 delicate 的 construction，对，
对，主要是其实结果还是最终的还是意味着东西嘛，最终处理到最后还是考虑是那个意味
因为你的
着那个
口音得
中心
出
方向的
来嘛，
东西。
对，
对，所以说更难的是现在就是下一步可能会考虑更高维，如果有什么应用的话，会考虑更高的那个中心方向，更高
你是
维数的
说你的口
中心方向。
音得是差距更多这样子？
对，
我可以想象那真的很难。
对，但是现在没有什么动机不是很足，就是看那个能得出什么东西不，就是新的东西。
对，其实这也是我今天一个问题，就是说，我今天听你的演讲，我数学体会、数学结构，我觉得是非常的深刻哦。那我现在想说，是不是有一个类似 normal form 的 model？比如说，不管是 different，比如说你是什么 Halo Map，或者 Logistic Map，或者是 PDE、ODE，这个东西刚好把你的这个 structure 给 capture，就是抓住。那
嗯，
我觉得大家就可以看到应用，那一方面大家可以透过这个 model 去理解你的 core idea。对对，
其实这东西应该是还是挺多，有几篇文章你就是在那种具体的那系统里找到过这东西，所以很好找。比如说，就你有一个混沌系统嘛，那就是你假设它一个混沌系统，它里边的你有两个周期点，它的 Lyapunov 指数它是不一样的，这应该
嗯，
是挺正
很常见，
常对吧？
对不对？但是
很
我跟你讲，
常见对吧？
我了解数学上很常见，但是给一个真实现在科学家、
是是是是，
化学家真的在研究的方程，是不是有这个结构？我跟你讲，根本就
对，它是都是，但小应该很常见对吧？你有两个不同指数的
没有。
周期，
对，
那它们互相连接起来，然后就成了一个一维化，
我知道，
是这样。
我很同意你。我现在只是说，如果我今天是想要有点反对跟我们吵架的，我就会说，你看超
嗯，
越数很常见，对不对？那你随便
对的。
找超越数给我，全程带动 number 给我，
派啊、E 啊，那除了这两个之外呢，你不要什么2倍 E 啊、3倍 E 啊。
对对对对对是，但就是能找到是最好的，所以说，
对啊，比如说我举个例子，假设我今天有一个方程式，我真的，比如说我真的要用你的东西，我必须要先证明什么？先要证明我有个 co-index one 的这种 heterogeneous connection。
嗯，
光是证明这件事情就 highly non-trivial 了。对，给一个具体的方程，就算我数值上看到它，我数值上就算看到这个东西，我要严格的证明这个东西
是挺难。就是我知道，就是新西兰那边有一组人，还有波兰，他们有一些人就在做这个，
新西兰那一组是谁？
具体的方程里边。
Osinga 吗？
对，他们就做了很多关于 Blender 啊，还是
可是我跟你讲一件事情，Osinga 他应该大部分时候没有在证明。
他只是你说只是找，
我觉得他就是给你 idea 说你可以这样那样，然后是这样，因为他这个人非常的 charming 嘛，你听他每次在那边，然后就说哦，好像证完了，没有，be careful，没有证之类的。
我就看他们找，就是基本每年都有1-2年都有一篇文章，也是关于这种还是在用 Cycle Blender 的东西。
那我可以方便问一下，说你现在做博后，你会就是延续这个方向，还是说你现在有开展新的？
我现在一个就是在做刚才那个最后提到那个问题，就是证明那个。
就是我有点忘了，不好意思。
就是说你在那个一个 tendency 就会找到找到另一个映射，另一个 map， 然后它的 constant family 它就在那个
什么贝亚格？
那个开始，对那个东西，还有一个就是做那个在那个就是 symplectic blender symplectic setting 那个里边，就是
you mean symplectic dynamics？
对symplectic dynamics， 我们考虑那个KM curves， 就是那种KM torus， 它有 stable 和 unstable manifold， 对吧？我们考虑这样的一个 torus， 它有一个 homoclinic， 然后我们研究它周围的 dynamics， 就目前就是在刚刚就已经证出来，就是在一维的那个 torus 下，就是怎么说就是个 circle， 就是 KM curves， 然后你可以发现这个东西，发现这个 symplectic blenders， 然后就是在 symplectic map 下的 blender， 然后它有一些别的性质，然后比如说有些是在那个天体力学里有一些应用，就是天体力学它们这东西在天体力学中不是就挺常见嘛，他们挺关心的。然后就是在那个 stable Goldstein， 就是那天跟Avila 他们就是聊一聊，他们在做那个 stable Goldstein， 就是在symplectic
stable
Goldstein， 就是那个
Goldstein，
对，就是你在那个space of symplectic diffeomorphism 里边，然后你能证明出就是一个 diffeomorphism， 它叫做 stably ergodic， 就是它做扰动之后还是 ergodic， 对吧？就这样的。然后他想证明是在
做扰动还是这样。
对，他们之前做的结果是就是对的是在那个 space of diffeomorphisms， 现在想做是大家更关心就是那个 space of symplectic diffeomorphisms， 这样的吧，能够有存在这种stable Goldstein 这样子，然后他们就要用刚好他们需要的东西就是我们现在正在做的东西，所以还挺巧的。对，如果说是，但是他们需要的是高维的，我们现在做的是一维的，对不对？就是说高维的话能推广的话，就是挺好的。
是啊，感觉有很多很多结构还可以等待发掘。对。
你现在就是回台湾很久了？
我2018年从柏林毕业，然后我就在台北的国家理论科学研究中心做博后。那个国家理论中心就是在台大，在台湾大学里面。然后我做3年博后，然后2021年在我的家乡台中，那有个中兴大学当助理教授。 然后我就今年服务3年之后，我今年8月1号来新竹的清华大学，不是北京清华，是
知
是
道
是新竹清华，
新竹的
新竹清华
哦，
大学，对对对，那对啊对啊，然后我自己的研究领域就是一开始做刚刚就是有一个方向就是做这种，
嗯
前面2个地方比较古典啊，存在性、稳定性分析，第3个比较新，就是做这种引入 control 做 stabilization 这种。然
嗯
后我还有另外一个研究方向是，就是就是很多人都在讲 bifurcation，那 bifurcation 基本上就是说你有调一个 parameter，然后调一调就看这个你的 face portrait 会不会有一些 topological change 嘛，
对
然后这个叫 bifurcation with parameter，因为你就是有个 parameter 给你
对
调这样。
对对对对，
那我最近我的指导教 Biano Fiedler 跟我的学长Stefan Dipscher，在2020年左右，他就是引入一个比较新的观念，但其实是相互相补的，就叫 bifurcation without parameter。
哦，对，我好像在网上见过这样他
对对对
的文章，
对对对。然后现在我做
说这个，
什么呢？因为我那个学长 Stefan 已经把这个，因为你比如说在 bifurcation with parameter 有 saddle node bifurcation，有后 bifurcation，有它跟 Bogdanov 一堆嘛。然后你在这个 bifurcation
对，
with parameter，你也可以相对应的去推广。
找相对应的那些，
对，但是它的 dynamic
哦
很不一样，我要强调，比如说后
不一
bifurcation
样，
有 PI solution with parameter，可是后 bifurcation without parameter 没有 periodic solution，它只有 heterocline orbit。
哦
譬如说这样，所以说你要注意，不要每次听到后补就觉得一定一大堆 periodic solution，careful。然后呢，我现在跟我合者在做一个蛮有意思的问题，这样子就是说，你现在假设你有后 bifurcation without parameter，然后我现在有个外在的参数叫 alpha，当我 alpha 等于0的时候，我就是有后 bifurcation without parameter，或是 bifurcation without parameter。然后我现在当然有个 parameter 嘛，现在有个 parameter 叫 alpha。然后我 alpha 一点点不等于0的时候，只要一旦它不等于0的时候，然后我这整个，因为你后 bifurcation without parameter 都有一个 manifold of equilibrium。OK， 有个因为你的这个 bifurcation 是用这个 manifold parameterization 去刻画，它没有 parameter，但它有这个 line 或是 curve of equilibrium。然后当你今天 alpha 不等于0的时候，一旦不等于0，这整个 manifold 就不见了。那请问这个时候你的 dynamic 是什么？对，所以简单讲，我们把这种现象称作 hybrid bifurcation，因为它就是一个 combination with bifurcation without parameter。一开始是 bifurcation without parameter，然后你有一个 external parameter alpha，然后你一脑洞一下，你整个那个 manifold 就不见了，然后你这个时候会出现一个 classical bifurcation，就 with parameter，所以它是一个 combination。那我们前阵子证明了，在这个情况下会有周期解。我们有一个找到周期解，就是说周期解有一个新的机制啊，就是这种 hybrid bifurcation。
但我想问一下，你没有参数的话，你怎么去定义这个 bifurcation？它是
很简单，
不是变化的时候才会有吗
？bifurcation 的 definition 就是no，OK，我现在讲一个比较观点，就是说，好，我现在假设有一个 ODE 好了，叫 x dot 的 f of x alpha， 可以吗？那 alpha 是参数。
对。
那其实我可以人为的加一个维度嘛，我就引入 alpha dot 等于0。
对对对，是的。
那你加入这个参数之后，你就假设你现在有个平面，中轴、横轴是 alpha， 纵轴是 x， 那你会发现在每个 alpha section 就都是一个 invariant plane 嘛，可以吗？这是一个trivial 性质，然后所以说 alpha 是一个 parameter， 因为 alpha dot 等于0，所以 locally 在这个 equilibrium 附近，你就得到一大堆 invariant foliation。那什么叫做 bifurcation without parameter 呢？就是 你现在你的 alpha dot 不等于0。
那是什么？不等于0。
alpha dot alpha prime alpha dot 就是 alpha 对时间 t 的微分。
哦，对。
对。对。这个时候它
你说现在是
0。
等于0，
对，
现在是不等于
0。等于0的话就是参数。
对对对对，现在是不等于0。
等于0的时候，它就不是 parameter，而且你要确保一件事哦，不管你的这个 coordinate change 是什么，你都不可能把它变成等于0啊。这样子，你先保证这件事情。那这个时候我们就说这个 alpha 它不是 parameter。
哦。
所以说这个时候本来你 alpha dot 等于0，你有一大堆这种 parallel foliation 是 invariant。当你今天 alpha dot 不等于0，你很有可能会产生这种 heterogeneity 从这里到这里，这样。
对对对。
那这个时候你会发现你不可能找到一个 invariant transverse foliation， 因为你每次找到一个 foliation， 它每次都会跑掉。这个就是跟你讲说，你不可能找到一个坐标变换，把 alpha dot 这个方程变成 alpha dot 等于
0。对对
对对对，所以这个意思就是所谓的 bifurcate without parameter。那最常见的 case 是这样子，你如果今天有一些微分方程哈，这个微分方程有对称性，譬如说你考虑2个物种的竞争，假设这2个物种它基本上你把这个物种1、物种2做个调换，方程还是一样。那你通常会发现你的方程式里面把所有的外在的参数固定住哦，你的方程的参数都固定住哦，你会发现你的 face plane 里面会有个 line of equilibrium， 就你有一条线，然后这条线上面每一个点都是 equilibrium， 那你当然就会考虑它的 linearization 嘛，在每个 point， 那你可以去算它 eigenvalue。
对。
OK， 那可能呢，这条线上这个点它是 normally stable， 就是说它当然有个 center direction， 但它的 normal direction 是这个conjunction stable， 然后可能在某一个 part 它的 normal direction 是 unstable。
哦。
那你就会发现什么？我现在所有外在的参数都控制住了，没有参数啦。可是你沿着这条线，你的那个
还在变化。
它会变化，所以这就是一个 bifurcation without parameter。对，那我们的研究就是这样子。你现在有个参数叫贝塔，好，那我说贝塔，你在贝塔等于0的时候，你有一个 line of equilibrium。然后我刚刚讲了，你现在外在参数都固定住，然后呢，你沿着这条线，你有从 normally stable 变成 normally unstable， 可以吗？所以所以说你有一个 bifurcation point 在这条线上 ，OK， 然后你有一条线，然后现在当你贝塔不等于0，一瞬间你整条线都不见了，你点也不见了。
哦。
那请问这个点到底它的 local dynamic 会怎么样？我们严格的证明，你这个点会变成一个 periodic orbit， 在一些条件下。
哦，这样子。
所以说你会发现这很有意思，因为以前的后 bifurcation 是你有一个 line of equilibrium， 然后你有个后 bifurcation 出来嘛。
对对。
就是你的
还在，
就你的 periodic orbit， 而且你的线从来都没有不见，一直在那。可是现在是你跑出去的时候，你根本线都不见了，你的那个你那些 equilibrium 全部都不见了。哎，对，
挺有意思
啊。对，你如果有兴趣，可以去看我们最近发那个 preprint 我们还在审呢，还没有投稿，还没有结果。但我觉得这很有意思，因为你看从庞卡内以来，你要怎么找周期节？你要不然就有庞卡内 Bendix， 我说 smooth dynamic system 啊，你要不然就后 bifurcation 啊，你要不然就 singular perturbation 啊，你要不然就monotone dynamic system 啊。或是 Coney Index 啊，这种 topological method， 然后你当然不止后 bifurcation， 你还有所谓一些 classical bifurcation， 什么 Targens、Bogdanov 也有，Hopf 也有一堆啦。那现在我们就是找到一个新的机制， 以前没有人想过，而且真的有
那是，
而且我们找到2个 application 是真的是科学家他在研究这个方程，是真的有这个结构。
那其实挺厉害的，
没有，
就像你说，能找到真的是系统里就有。
对，没有，因为我们本来为
不仅仅是
什么研究这个 hybrid bifurcation，不是因为我们对这个结构有兴趣，是因为我们有一个具体的问题，然后这个具体的问题逼我们去研究一般的结构。
这样子，那
对对对，
挺好的，他发现东西。
对啊，然后对，所以但是我们的条件比较容易 check 的，就是我们的条件都是非常 local 的条件，可是 Hitoken Orbit 是一个超级 global 的条件，因为你这个可以离很远的。
啊，确实是。
那比如说，我觉得你如果去跟 PD 的人聊天，你跟他讲说我要找一个 Hitoken Orbit highly non-trivial，因为我们永远都知道 locally，比如我现在有 equilibrium，我知道 local stable manifold、local unstable manifold，我甚至也可以知道它的 direction 或者它的 dimension，然后现在要怎么 connect，那你就会说我们有 Malinkoff integral，我们有 shooting method，我跟你讲，每一个东西都可以发 paper 啦。然后你如果今天是一些有意义的方程是什么跑上equation，那个什么薛定谔跑上 Euler 跑上，那你都可以发什么 CPAM 嘛，就是 highly non 这种，对啊。那我可以方便问一下东城，这里你博后还要做多久？还是会想要在英国、欧洲？
我升了几个，就是升了几个教职了今年，然后看
你有申请
结果。
正在申请吗？
对，正在申请，已经就在这边。
那你是全世界找，还是有锁定一些地区？
我是在英国找，然后北京、上海找，就都投了，反正。
然后是 OK，了解。对，祝你都顺利。对，
谢谢。
我觉得你的研究很棒，对，很不错。对啊，
你的也很棒，都挺好的。
啊，那就看看有机会有没有在哪一些地方长久，或者你有机会来台湾，或者来访问，都跟我说一声。对，
行啊，好啊，
我们台湾可能跟你比较近的领域没有那么多啦，但是你这个是一个动力系统很 fundamental 的结构的研究，我觉得大家都是会受益匪浅的。
谢谢。
OK， 好，最后的话就是，如果有听众他跟你要投影片，他可能会写信给你，那你就决定你要不要拿。可是这个有一些人他可能要投影片，他会散播出去，所以你就如果你的东西不想要被散播出去，你就直接忽略这个 email。对，你就可以不用回，没有关系。
好的，没关系，这已经是发表了，没关系。
OK， 好，东城，谢谢哦，那我们就
谢谢，
之后见。OK，谢谢，
之后见，有机会见，拜拜，再见。
拜拜。